Okay, let's dive right into this explainer. Today we're going on a seriously fascinating journey, straight into the mind of artificial intelligence. We are going to explore exactly how AI scales up its intelligence, evolving from simple rule-based decision mechanisms to these massive, collaborative meta-organisms that power the most advanced predictive models in the world today. If you've ever wondered how raw data translates into highly accurate predictions, well, you're definitely in the right place.
Here's a quick look at our roadmap for today. We'll start simple with the humble decision tree, jump into bagging and random forests, and then tackle boosting. After that, we'll look at stacking, and finally wrap things up with continual training. Let's get to it.
So it really all starts with one fundamental question. How on earth does an AI actually make a decision? You see, whenever we build a predictive model, we're constantly fighting this tug of war known as the bias-variance trade-off. If a model is too simple, it has high bias. It underfits and totally misses the underlying patterns. But if it's too complex, it has high variance, which essentially means it memorizes the training data, but fails completely when it sees fresh, real-world data. To see how we actually solve this balancing act, let's introduce our very first algorithm.
Section 1. The humble decision tree, the absolute building block of AI.
What makes the decision tree so incredibly cool is that it's a non-parametric model. In plain English, that means it doesn't just assume our data follows some neat, predefined mathematical shape, like a perfectly straight line. Instead, its capacity grows dynamically with the data itself. It builds a set of conditional rules, recursively splitting up the feature space based on specific thresholds to maximize what we call subset purity.
To intuitively wrap our heads around how the algorithm measures the messiness of a dataset, picture a bucket, or a node, containing 6 items in Class A and 4 items in Class B. It's a mix, right? It's impure. The algorithm uses a neat metric called Gini impurity to evaluate how often a randomly chosen element from this set would be incorrectly labeled. By crunching these proportions, the decision tree aims to find the optimal split that lowers this impurity, essentially separating the data into new branches that are as pure and uniform as possible.
Let's make this real and see how it builds into practical decision boundaries. Imagine we're trying to predict if a student is going to pass a course. Step 1. The tree checks a feature, say, is hours studied greater than 3? That split mathematically reduces the messiness. Step 2. For that resulting group, it checks another feature, like class attendance. Step 3. It hits a leaf node and makes a final prediction of pass or fail based on the majority class right there in that node. It's completely transparent and super easy to interpret.
But, like any good hero, the decision tree has a fatal flaw. While it's super intuitive, a single deep decision tree is highly prone to overfitting and instability. It has incredibly high variance. It will literally memorize the random noise and weird outliers in your training dataset just to create perfectly pure leaf nodes. And honestly, worse yet, because it relies on greedy sequential splits, if your data shifts even slightly, boom, the entire structure of the tree can change completely. It's just too unstable to use on its own for really complex data.
Moving on to Section 2, bagging and random forests, parallel ensembles.
So how do we actually fix that fatal flaw? Well, our first massive evolutionary leap is combining models in parallel. The concept of bagging, which stands for bootstrap aggregating, is perfectly captured right here. Bagging is like aggregating independent weather forecasts. Think about it. If you ask just one single meteorologist, their specific bias might give you a terrible forecast. But if you take multiple independent bootstrap samples of your data, train a separate decision tree on each sample, and average their predictions together, you smooth out all that noise. This brilliantly reduces variance and stabilizes the overall model, all without increasing bias.
But wait, we can do even better than that. Let's contrast standard bagging with random forests. In standard bagging, every single tree evaluates all the available features for its splits. So if one feature is just a huge, strong predictor, almost every tree is going to use it for the very first split. That makes all your trees highly correlated. Random forests introduce this incredibly clever twist. At every single split, the algorithm only looks at a random subset of features. This forces the trees to explore totally different paths and stops dominant features from taking over the whole show. It creates a much more diverse, robust ensemble.
Section 3, boosting, learning from mistakes.
Okay, so we've seen what happens when we work in parallel. But what if we train our models sequentially? I absolutely love this analogy. Boosting is like a teacher correcting a student's specific mistakes one at a time. Instead of building massive, deep, independent trees, boosting starts with a very weak learner. We're talking a shallow decision tree that might only make 1 or 2 splits. Then, the next tree comes along, looks specifically at the residual errors, the mistakes of the previous tree, and tries to correct them. It systematically zeroes in on the hardest-to-predict data points, iteratively squashing down errors over time.
And this brilliantly illustrates the contrast here. Bagging uses these deep, strong trees, trains them in parallel, and is purpose-built to reduce variance. Boosting, on the other hand, uses shallow, weak learners, trains them sequentially, and is designed primarily to crush bias. They take exact opposite approaches to that initial bias-variance tug-of-war we talked about, yet both of them result in absolutely phenomenal predictive models.
Because boosting is just so incredibly effective, developers have created highly optimized versions known as gradient-boosted decision trees. These are the absolute heavyweights. Literally, these are the algorithms you constantly see winning real-world data science competitions. You've got XGBoost, famous for its raw speed, parallel processing, and built-in regulation. Then there's LightGBM, which uses leafwise tree growth to be insanely efficient for massive datasets. XGBoost is uniquely awesome because it natively handles categorical data without needing complex preprocessing. And AdaBoost, a total classic, focuses strictly on adjusting the weights of misclassified instances as it goes.
All right, Section 4, Stacking, the ultimate panel. Enter the meta-learner.
We've done parallel, and we've done sequential. That brings us to stacking, which is basically the top tier of our workplace analogy. Stacking, or stacked generalization, combines predictions in a completely different way. Instead of just relying on trees, imagine assembling the ultimate diverse panel of experts. Maybe you grab a decision tree, a support vector machine, and a linear logistic regression model. They all review the data and generate their own individual predictions. Then, those predictions are handed straight to a head analyst, known as the meta-learner. This meta-learner is explicitly trained to figure out exactly how to optimally weigh and combine the outputs of those diverse base models to maximize overall accuracy and generalization.
So, the crucial point when we compare our 3 evolutionary leaps side by side is how they combine their outputs. Bagging relies on a simple majority vote or an average to reduce variance. Boosting zeroes in on reducing bias by using a weighted combination where each new model fixes the last one's mistakes. And stacking focuses on maximizing generalization by using that dedicated meta-learner to make the final call based on outputs from totally different types of models.
Finally, Section 5, Continual Training, Adapting to the Future. Now, before we look too far ahead into the future, we have to talk about keeping these current meta-organisms in check. To stop these massive ensembles from just mindlessly memorizing the data and overfitting, we have to impose strict structural rules. We call this regularization. The techniques include pruning away weak branches that just don't lower impurity enough. We can set a maximum depth so the trees don't grow forever. In boosting, we adjust the learning rate, carefully scaling down the contribution of each new tree so the model learns slowly and robustly. We can even slap mathematical penalties like L1 or L2 directly onto the leaf weights to heavily penalize anything that gets overly complex.
But here's the catch. Even perfectly regularized models face a massive looming challenge out in the wild, the continual training problem. You see, traditional decision trees and their ensembles are batch trained. They require all their training data to be sitting there at once to calculate those optimal Gini impurity splits. They are fundamentally rigid, so when new streaming data continuously arrives, you can't just easily fine-tune a fixed decision tree. If you try to just awkwardly glue on new branches, you risk severe overfitting. But completely rebuilding a massive ensemble from scratch every single time new data arrives, that is computationally exhausting.
To navigate this, developers use some incredibly clever workarounds to let models learn incrementally. Take Huffington trees, for instance. These are online decision trees that use statistical bounds to confidently split nodes on the fly, right as the data is streaming in. Then you have things like online random forests, which gradually update or replace older trees without destroying the whole ensemble. And for gradient boosting, developers utilize warm starting, which is basically continuing training from a previously fitted state, or stochastic gradient boosting to smoothly incorporate new batches of data.
And that brings us to the end of our explainer. We've traced this incredible evolution from a single shaky decision tree, all the way to parallel random forests that conquer variance, sequential boosting algorithms that absolutely obliterate bias, and finally, to stacked panels of diverse AI experts. But as the real world moves faster and data literally never stops flowing, how will our models evolve to truly never stop learning? It's a profound engineering challenge, and it's pushing the absolute boundaries of what artificial intelligence can do. Thanks so much for joining me today, and I really hope this sparked your curiosity to dive even deeper into the mechanics of machine learning.